Okay. Yeah, welcome back. Last time we stopped with the SystemC basic chapter, and now we will start with the SystemC advanced chapter, where we also look under the hood of SystemC how things are built, and we will also write our own components. Yeah, so that's again the big picture. So we learned so far about the simulation kernel, about events, sensitivity, and hierarchy. And today we want to look into data types and then on channels on interfaces. And this is the most interesting part actually, how this is solved in SystemC. And the rest will come later. So first, let's very quickly go through the data types. So of course we are in C++, yeah. So we can use all the C++ data types that are there. Bool, character, short int, up to unsigned long int or whatever. Yeah. So in SystemC you can just use these data types. But in SystemC we have more. For example, in VHDL we have standard logic where we have uninitialized, unknown, 0, 1, high impedance, weak unknown, and so on and so forth. So the C++ data types are not enough if you want to model hardware. Yeah? So we need something to express also unknown, uninitialized, or high impedance. And SystemC has something similar. There's a logic data type which is called SC-bit, but actually that's deprecated. We should use now bool. So this is just for logic data types. And there is a Boolean vector that we can use, and it's templated, so we can define a length for that. Yeah, so we can have a bit vector with 2 bits, and then we can assign also to it a decimal number, but we can also assign a string actually. Also that would work. And there are also some interesting functions there. I think that's interesting. You have this AND reduce, or this, I called it here X reduce. You can also have an OR reduce. That means that's a bitwise AND of all the booleans in that vector. So you can just reduce it to 1 bit. That's kind of handy for some applications. You can also specify a range. So if you want to, you have a 6-bit vector here, and then from bit 0 to bit 3, you want to write something, and the rest shouldn't be overwritten. You can basically do that with this range operator here. If you just want to print it out, you can also even make it short like this, or also use range. Or you can also get a single bit just by addressing it like an array. All of this works and is somehow overloaded. Yeah, you can also concatenate. For example, here we take these 4 bits of D, which are basically 1, 1, 1, and then A also was 1, 1, 1 here. Here we did an OR. And then you can just concatenate that, and then you get again 6 bits, 4 and 2 is 6. So also this would work. Yeah? But I don't want to go so much into detail because that you can look up basically in the SystemC reference manual. Yeah, but there's SC logic where you then also get features like unknown and high impedance. So it's not just 0 and 1, you can also have 2 additional states. And it's not like in VHDL that we have 9 different states. Here we have just 4, but okay, if you would need more, you could also derive from this SC logic your own logic class, and then you can put even more states if you need it. Yeah? But for the standard, they said, okay, we just use X, 0, 1, and high impedance. Okay, and then we have the logic vector, which is then basically a vector of SC logic, and this is pretty similar to the bit vector. And so it makes also then sense to have this high impedance, for example, if you have a tri-state bus system or something like that, that also there the logic is computed correctly. Okay, but as I said, you can look that up in the reference manual also. Yeah, then a quick reminder, we have fixed point numbers, especially in the two's complement. This is also a topic that we discuss in Rechenanlagen or Digitaltechnik. You can specify a specific amount of bits before the decimal point and then a specific amount of bits after the decimal point. And then, for example, you can express a number like pi with an appropriate accuracy. So if you want to be more accurate, then you have to add more digits after the decimal point. Yeah, so that means here that's the 1, that's 2, that's 4, and so on and so forth. And here you have then basically half, a quarter, and so on and so forth. And then you can build also fixed point numbers. And also that can be done in SystemC. First of all, we have just integers with scint. So why do we have this? Because we want to have an arbitrary width. Yeah, so we want maybe an integer in two's complement that has only 6-bit, for example. Yeah. Because maybe we want to build an accelerator for a neural network that just has an accuracy of 6 bits, so something like that. Or even more. So we can, with SC big int, we can also say, okay, we want to have an integer that has 512 bits. Yeah, also this would work. So the normal scint is limited to the 64 bits because then this is exploiting the normal 64-bit system of our architecture of the host. But it's also possible with this special data type to have a bigger width, and then, of course, the simulation will be slower. And that's also, again, our picture here. I saw it. And the reason for that is that we have to compose, for example, 512-bit out of several 64 bits, and then we have to do a lot of calculations, and this makes it basically slower if we use such a data type. Yes?
Is it possible to use any number like 17, or must it be to the power of 2?
No, you can use any. Yeah, so you can, before I said 6, but you can also have 17. That also would work. Yeah. Depending on your accuracy, and that's often also part of the design space exploration process. So we want to know which bit width should we use in a specific hardware architecture such that we get still accurate results, but we want to keep the area small. Yeah, so we see that in the tape outs of our RISC-V CPU. If we tape out it as a 16-bit CPU, then it's much, much smaller compared to if we tape it out as a 32-bit CPU, because then, of course, the number of data lines that you need is doubling. Yeah? So that has a high influence on the size also of your chip. And therefore, you want to make it as small enough that you still get accurate results, That's also a trade-off. And here's the other trade-off, that if you use such a data structure that, for example, with 512, then your simulation will be a little bit slower. No? Okay, so that was integer. Now let's go to fixed point. And also this works with SystemC, and actually we have there 4 options. So we have unsigned fixed point, and this is just another way to specify it. So this is the templated way, and this is with constructor arguments. And then you have fixed point, which is not necessarily unsigned. And this is an example now for an unsigned fixed point, and then you specify in the template arguments here 7 and 4, whereas the 7 here means the total length of this, or word length, and 4 basically tells you the integer part, so the part before the decimal point. And then implicitly it's clear that if you have 7, 4, then you have 3 digits after the decimal point. And then we have some specialties. So it's quantization mode. That's basically how this is rounded. And then the overflow mode, this is also interesting. So if you reach basically, for example, the full vector with ones here, that's the biggest number that you can basically, in this unsigned setting, the biggest number that you can show, everything is 1. And if you add then an additional 1, what would happen normally? You would get an overflow. Then everything basically gets 0. But you can specify here also set, so that the default is wrap. Yeah, so if all the bits here are 1s and you add a 1, then everything becomes 0. That's the normal thing. But if you have saturation here, it would basically stay at all 1. Yes?
So the difference between unsigned and signed, if you have a signed number, do you have to take into account the first bit is occupied by the sign? Or, for example, if you have signed 7, 4, then you would have only 3 bits whole number, or would you have the full 4 and sign as extra?
So to be honest, I don't know it. I have to look it up. Therefore, I also wrote there, look in the SystemC standard. But I think it would make sense if you have then the sign bit here. But unfortunately, I put here in the example only the unsigned version. But it might be that the sign bit is then also reserved, or it's implicitly there. I don't know it. Maybe 10 years ago when I did the slides, I was aware of it. But now, in the meanwhile, I forgot it maybe. But let's check if I have it in the notes. Could be that I have it still in the notes here. No, it's not there. So I have to look it up. Yeah? But you can also find it in the reference manual then. Maybe you can just, you have your laptop in front of you, maybe you can just look it up and then we know it. But this is interesting that we can saturate a value. That we can say, okay, if we add more and more and more, it will never go over the maximum value. And that makes sense in several scenarios where you don't want to have an overflow. That might be signal processing, or that might also be a neural network, for example. Yeah. Okay, but just details. I don't want to spend so much time on this because that's something you can read in the standard, and it's not so difficult then to understand. Okay, so let's go to the more interesting topic, which is channels and interfaces. And there we need something from object-oriented programming, which is polymorphism. And this is just a recall. I don't know if Derek had discussed with you again all the C++ details. But at the end, what is the idea of polymorphism? We have a well-defined interface, and we have basically then abstract class, in this case, for example, shape, and then we can have several classes that are derived from this one, and then we force them to implement a specific function. Yeah? So, for example, here we have rectangle and triangle, and they, if you want to compute the area of those, they have different ways to calculate the area, right? So, for the rectangle, it's then width times the height, and for the triangle, we have to divide this by 2, basically. So that's the idea. But if we implement this with this concept, that we have this abstract base class, then we can treat them with a pointer as a rectangle or triangle. We can treat them just as a shape, and we don't care if it's a triangle or not. And this is this concept of polymorphism. Yeah? I think you know that also from probably Java or any other programming languages. So the most important thing is we define interfaces, and this is also what we need if we model in SystemC components and we want to communicate with different components. And this is done by defining interfaces and especially then channels. Yeah, so let's have a closer look on this, basically the channels. So in VHDL and Verilog we have signals for the communication, and SystemC has generalized this a little bit more. It's not only a signal, a channel could be anything. So it could be also a queue, for example. So in SystemC, a signal is just a special case of a channel. Yeah? And channels separate communication from functionality. So we have here a component that has a thread, SystemC thread, that does something. And there's another module that also has a thread that also does something, and they can communicate with each other by a signal. And the signal is just a channel, yeah? So this is the channel here, and the channel this is basically a container for communication protocols and synchronization events. And each channel has an interface. So this is a set of pure virtual methods. And the channel basically is, or the interface specifies that. And in this case, for a signal, it would be the write and also the read methods that we have used already. Yeah? So we have used already signals in the previous examples. And yeah, so we define the interface, and if we then create a channel, we derive from this interface. And also the modules need to know which interface of this port they have, because then we make sure that we can only connect here channels that implement this interface. Yeah? And that also makes sense because we can exchange that. So we can have an interface class, an abstract interface class for a signal or general for communication, and this could be used by a signal but also by a FIFO queue, for example. And then we can exchange that. So we can use the same modules, but we can exchange the medium in between. We could say this is a signal, this is a queue, or this is a queue with some arbitration or whatever. And this makes it pretty convenient. We will see that in some minutes when I will create my own custom signal or channel. Yeah, and then modules access the channels via these bounded ports. Yeah? So this just calls a write function, but the module does not know, is this now a signal or is it a FIFO? Because for both, it's the interface right, or the method in the interface is right. And then only if you bind the things together, you will basically then specify if it should be a signal or a FIFO, for example. And this is cool because the module actually does not know it. And this is pretty similar like in biology. So you have basically here your synapse thing, and then there is some muscle cell, and there are some chemical reactions in between. I don't have any clue about biology, but the interesting thing is that the synapse, so the nerve cell here, stimulates the muscle, but the cell here doesn't know what the muscle will do, and also the muscle doesn't know why it's actually stimulated. But then you put it together, and then there is a system now that works. And this is similar here. So it's very important that this module doesn't know what's actually happening inside here. So you have only a defined interface, and that's it. Okay, so let's have a quick look into the SystemC standard. There you can see this. There is a SC signal in interface, and there is a SC signal write interface, and this is a very small class. Okay, there's a little bit in front and in back as well, but I removed that. The most important thing is that you just define there should be a read method, and there should be a write method. And then there is a SC signal in-out interface that just inherits from those, and everything is also templated. And then the SC signal class, in short, will then implement, or will be again, or will inherit again from this interface class, and then it has to implement read and write. And there's also something called SC prime channel, where this we will discuss a little bit later. But that's the main idea. And there you could also write then a FIFO. And that's, I think, what we will do right now. Okay, so interfaces are the collection of pure function methods. Interfaces can be composed also by inheritance. And then, a channel has to implement these virtual functions. Okay. This is then when you use it. So if you do some binding, if you write or if you create then a port like this in your module, what we did so far was we used SC in and SC out. So that's what we have done in the previous examples. And this is just a shortcut for this. So you have for an input port, you create an SC port with the template of this interface. And it's double template. So it's here integer and then the interface. And also for the output port, you would write it like this. And this is nothing else than this here. So you can. This is more, of course, easier and more convenient for us, but at the end, it's basically this. And you can there even specify more. So if you really use SC port, you can make it short like this, or even shorter. But you can also give here some policies. So for example, this N is optional. You can say this is the maximum number of channels that I want to connect to this port. And there is the policy at the end where you say, okay, one or more bound. That means at least one should be bound. You can also say 0 or more bound. That means, okay, I do not care if nothing is connected to this port. also fine. Or you have to say all of these endports must be bound. Yeah? So this is just, and then the simulation will not start basically if this policy is not fulfilled. Yeah? Exactly, because then you get these binding errors. Yeah? And there is one difference which is sometimes a little bit tricky. If you define it like this with scport, then you have to use the arrow operator. If you use the short version, then you have to use the dot operator. Because here we work with a pointer, and here this is somehow encapsulated. Yeah. Okay, then the binding, I think that's also something that we have seen already last time. You can use this bind method, and then we make sure that this channel, which is a signal, is then bound to this port and that port and so on and so forth. Yeah, this is done by the bind method. Good. Okay. Yes?
So is this bind, it has the same effect as what you see for the XOR, where there's no bind?
Yes. That's the same thing. It's just shorter, but I recommend always to do it like this, because then you see explicitly, okay, this is a bind. But I think also last time we discussed that already, that we do not need this keyword here. Yeah. But good remark to remember again. Okay, so now I want to build with you a channel. And I'm not using SystemC, the SystemC FIFO, which is already there. We will build our own FIFO that you understand how it works. Yeah, so because SystemC allows you to create channels with your needs, and that also will be part of one exercise where we build then P-tree nets, but more to that later. So the interface methods are allowed to block, and that means internally we can call wait. Yeah? But that implies also that we can only call wait and read from SE threads, because in SE methods we are not allowed to call wait statements. That's the reason why only SE threads could be used here. But okay, this is now a constraint that we have to accept. But for this exercise here, I think it's fine. So what is our goal? We have to implement a simple FIFO where we have a module that is a producer, and the producer can put something into the FIFO. And then after some time, maybe the FIFO is full or not, whatever. And there we have the consumer that consumes something from the FIFO. And the FIFO should implement blocking read and blocking write semantics. Yeah, so that blocking read means if the FIFO is empty, the consumer has to wait until something is in there, and then it can continue. That's a blocking read. Blocking write means that if the FIFO is full, the producer is not allowed to send something into the FIFO until it has some free space again. Yeah, and then the producer has to wait. That's what we mean with blocking read and blocking write. Yeah, and before we create the FIFO, there should also be the FIFO interface that should have pure virtual functions for read and write. Yeah, here for write and there for read. Okay, so let's try to build that. And therefore I switch again to my VS Code. Maybe. So it's maybe better if we are on this dark theme that we. But don't start to sleep now. Okay, so this is the example that we did last time, where we built this custom adder. And I will just probably just comment this out and then use that. Okay, first of all, we need to implement the interface. Can you read it? It's okay? Or it's too small? Can make it.
Maybe zoom a bit more.
So, better? Okay. The problem is that probably then we don't get everything on the screen, but okay, let's try. So first of all, we need the interface. And I'm lazy, so I'm using this. The interface is also a class, simple FIFO, or let's do it like here in the script. Simple FIFO interface, and we have to derive it from SC interface. And since it's a class, we need a semicolon. And we also want to template this. So the FIFO should be able to, that we put there integer, bool, or whatever. It could also be a class. Yeah. Therefore, we need to template it. Yeah, question?
I think public SC interface instead of SC.
Yes, that's correct. Thanks. But the compiler would tell us later on anyway what's wrong. But we want to template that. We make a class template here so that we can put any class. And then we make now two methods. And this should return from the data type T some read. But as the method should be called read, but it returns something from type T. And this should be, of course, virtual. And we define it then like this. So we cannot create an instance of this class because, wouldn't work. And then we would have the write method as well. How would that be? Not 100%. So are we get something from the method or do we put something into the method? For read, we get something back, but for write, we want to put something in, right? So it's a void method, right? And we put something in here. Yeah. And that's our interface. And because of that, we know which channels we can connect then to which modules later on. Yeah, so the FIFO will be accessed by read and write methods, and that's specified with that simple interface. So, now let's build the FIFO itself. It's again a templated class, similar to this. So I can just copy that. Simple FIFO. And now we derive this, or we have to inherit from something. And this is the simple FIFO interface. And we also forward then here this data type. Yes. And we have to end this with a semicolon. Okay, so the FIFO itself, we need a data structure to store the data that we put in the FIFO. What would you use for this in C++? Yeah, maybe there, back.
Probably I think it's
Yeah, but a queue, I think, is good if we would use that. So we have to include queue. Yeah. So maybe let's just check if that still compiles here. Otherwise, we have probably some. Oh no, no, we won't. It won't compile if we do it like this, I would say. But maybe like this. Now it compiled everything. Yeah, okay, that's also correct because there's no SC main which is required. Yeah. Okay, that's good. It compiles already. So, and now we need the data structure. So we do some private I used namespace std already in the beginning. So actually Q should be enough. So Q, and I just call that FIFO. That's the data structure where we will store our data. Yeah. Then we need a bunch of events as well, because we have this blocking read and blocking write semantic, and we need events basically to unblock. Yeah. And therefore we create here an SC event. One we call written event. This is there to unblock the blocking read. And there is then the read event. This is when we have the blocking write. So if the queue is full and we have consumed something, then we have to notify the waiting producer that it's free again. And therefore we need these events. Yeah? That's the reason. But you will see that in a second. Okay, that's okay. Maybe we could also specify something like unsigned signet int, unsigned int max size, because we want to give this queue a specific size as well. Yeah? We need then also, okay, now it's full, and this is specified by the maximum size. And we can specify this then in the constructor. So we have the constructor here, simple FIFO. That should get the size, and we could give it a default value, I don't know, 16, whatever. And then we initialize max size with this size. And that's the constructor. Yeah? So we keep it simple, small. Okay, so if I now want to compile this, actually it shouldn't work. Because actually it should complain about interesting. I always thought that this will complain, but probably because it's not yet used. Yeah, so then it's probably not complaining because it's not used anyway. So if we make now an instance here of the simple FIFO, and we take integer as the template, and we make it with a depth of 4 or maximum queue size of 4. So let's see. Okay, this does not compile. Okay, makes sense. Because now it complains that these methods are not implemented. Yeah, unimplemented pure virtual method read in simple FIFO. And this is what we still miss to have a working FIFO. Yeah. So that means we have to implement the read function here. And we have to implement the write function, like this. No? Okay. Yeah, let's think a little bit about it. So we want to read. So if you think, maybe it's better to draw it here again. So we have the producer, yeah, with the port, and then we have our channel here that contains the FIFO. Or had some spaces empty. And there we have the consumer. And now we implement read. Read was here. And there's write. Yeah, there we put something in, and there we get something out of it. So what is probably the first thing that we have to check when we do a read? Yes?
You have to check that nothing is writing currently to it, that flag basically, or basically that it's not locked.
Almost. So I don't want to talk about race conditions here right now. So let's assume the FIFO is already in a stable state. So what would lock mean then? So lock is okay, or it's blocking, yeah. But what would be the condition? So when are we not allowed to read, actually? Yeah. Exactly, yeah. So if the queue is empty, we should block here. And that's the first thing that we have to check in this read method. Yeah, so we need the if statement, and then we use the standard queue from C++, and there is this empty method. So if this FIFO is empty, what should we do? We block, right? So we have to wait. And for what are we waiting? Yeah?
We are waiting for something in the FIFO.
Exactly. So we wait for something has been written to the FIFO. And for that we have created this event. Okay? So we wait, for the written event. That's the idea. So later on in the write function, when something has been written to the queue, we will fire this event, and this gets automatically unblocked. Yeah? So if the consumer, and there's a SystemC thread that calls this read method, and the queue here, the FIFO is empty, then implicitly here a wait will be called, and this process will stop the execution. Yeah? And then wait means nothing else to, okay, we go back to the SystemC kernel and something else is simulated. That's the semantic of the wait. So wait always gives the control back to the SystemC kernel to simulate other things. Okay. So we are just blocked here, so this is just a lock, yeah, as you mentioned. But let's assume the FIFO is not empty, we can just continue. And what do we do? So we get the value of the front of the FIFO, and then we can remove it. I'm not sure, maybe this is also, there's probably a method to do both in one step, so maybe also pop returns it, I'm not 100% sure. But I think that makes it clear, okay, let's get the value and then remove it from the FIFO. And then we return it. No? Okay, so I keep here something intentionally open because there, okay, let's ChatGPT do it. Okay, no, we don't want that. But actually I disabled it for this. Interesting. Okay, but let's continue now with the write. So for the write, we get also some value. And that's similar to the read. Also, there might be a blocking situation. What's the blocking situation for the write? When we look at the queue? Yeah?
Yeah, if FIFO and full.
Exactly. So if we have 4 elements in there, then we have to block also. So there we need another if statement. If FIFO.size is equal to max size. Yeah, and then? Yeah.
We wait until read event?
Exactly. Yeah, this is the other event. Okay, so what does write mean? So if we are allowed to write, so we make just FIFO push, and then we put the value in it. And now, are we done? Yeah. So we make written event dot notify, and then in SC0 time. So if we want to model maybe also some write delay or something like that, we could also put there 10 nanoseconds or whatever. Yeah? But now let's just say, let's do it immediately. Yeah? Okay, but that's not all, because also here we are blocked now. We also have to unblock this, and this, oh no, I don't want to delegate it. This we have to do here. So there's also this read event where we also have to notify. Yeah. And that's it. That's a FIFO that inherits from this interface. And now we have to write just the producer and the consumer to make the example complete. So let's first check if that still compiles. No. There is a semicolon missing here. That looks good. Okay, so it compiles, so no syntax errors. And this stuff I just remove. So now let's implement the producer first. So we make now SC module as we know it. And an SC module gets the name producer. And this is also a class, don't forget the semicolon. And now there comes the SC port now. So we create an SC port that is from type simple FIFO, and that's not 100% correct. It's actually simple FIFO interface, yeah? Because we just need the interface. We don't care about the implementation, because maybe we want to have a more sophisticated FIFO later on that has the same interface but different behavior, okay? And then we can just exchange that here in the main. So we can have a simple FIFO, we can instantiate that here, but then we can have also a complex FIFO, and we don't have to change the modules here because it uses the same interface maybe. So maybe FIFO interface would be the better name. And then we can have simple FIFO and complex FIFO as implementation. Yeah, so this module then also, let's say, is int, but also this could be templated again. So we could also template this SC module, but okay, let's keep it simple. So now we have this political incorrect naming here, which I have not yet updated, so but I just keep it. So we have here master. And later on we will have a port that is called slave. I don't know, maybe you have better ideas. Then we could also change it. So SCCTOR. And in the constructor that has the same name, producer, as the class itself. And there will be a SC thread, which we call process. And then there is void process. That's the actual SC thread implementation. And there we have you remember, in threads we are allowed to have endless loops. And then we say here, okay, wait for 1 nanosecond. And then write to the port. Or we could also call it just port. So write with the pointer, right? And then we write there, I don't know, 10. Could also be a random number, whatever. Yeah? Or we could also call it out, maybe that's easier. So there's the output port, we write. And that's the producer. And the producer does this now endlessly. Yeah? So there is no actual end. But no problem, we can limit the simulation time in some other way. Okay, and then we need a consumer. And the consumer is pretty similar. We call this port then in. And you see already why in SystemC signals we have this 2 interfaces for in and out, and here we just share it, so you cannot really distinguish if this is an in or output port, because it implements both of the methods. But okay, for our simple example here, that's, I think, okay. And also the consumer has a process, and this process has also something. Oops. So while true, and there maybe we wait for 4 nanoseconds. So you see already the consumer is consuming much slower than the producer is producing. Yeah, so there it produces in 1 nanoseconds and this one in 4. And that's the reason why it will be stalling. So we will reach a point then where the queue is full, and then the producer has to throttle down the speed, actually, because it has to wait all the time. Yeah. So we also need to do something with the data. So we print out slave read. So we get the data and then we print it. Okay. Yeah.
We don't define slave.
It's not slave, it's in, right? Yeah. So this should be this port. So let's compile it. There's still a semicolon missing. I'm not used to program so much C++ anymore. Doing a lot of stuff in Python nowadays. So, so let's see if it works, because I think we are not 100% finished yet, but let's see. Okay, so let's create a producer. Let's call it Pro. And then a consumer. Let's just call it con. And then we have our channel, and now we have to bind the things together. So pro dot out dot bind, and now our FIFO is called channel. So now we connected our channel to this port. Yeah. And then consumer in dot bind channel. Yeah, because that's the channel from both sides. Yeah. So also connected. And then I limit the simulation runtime to probably 10 nanoseconds. Yeah. And now let's see what happens if we run this. Yeah, so in 10 nanoseconds, you can consume twice. Yeah. So we have to probably increase then all of this. So we could also maybe show, if you write to the queue, we could probably print out the size as well. Does it make sense to make it in the beginning or at the end? Maybe we do it like this. No, we don't need see out, write, and then we print the number of elements in the queue. And we do the same thing after we do a read. And then we see how the queue fills and so on and so forth. Yeah, so you see, we write, and then there is a read happening, and then that reduces the amount. Yeah? And then it's consumed here. Yeah? So then again, write, then we have 4 in it, and then we consume again a read, and then we have again 4. It's now actually interesting to see a little bit more. So let's maybe just make, 16 nanoseconds. Again. So now you see probably a little bit more. So write, then we consume again, it's again 3. But then we write, and then you see that we are stalling. So we cannot write anymore with the same slope or rate. And if you run this then even longer, maybe for 100, then you will see that we get this kind of equilibrium point, or how you call it, that this slow consumer will basically tell also the write or the producer implicitly what is the frequency, because it stalls, because the queue is full. Yeah? And if you make the queue now bigger, then this situation where we only have this ping pong between write and read will be delayed, of course. Yeah? And with that simple stuff, you can already simulate a lot of interesting things. Yeah. Okay, yeah, that's the idea. So, yeah, to summarize again. First of all, we have created this interface that just defines, okay, a FIFO will have a method that is called read and a method that is called write. And then we implemented the FIFO itself, and it inherits from this interface. And yeah, we can manage all of this basically by calling wait statements to get things synchronized. But that implies that we have to use SC threads here. Yeah? Otherwise it won't work, because if I have an SC method here, then it will complain and tell me, oh, wait is only allowed in threads and not in methods. Yeah? So that's important to remember. Yeah, so always use SC threads in this situation. But what if we want to use methods? And that's what we will discuss next, I guess. Yeah? So let's go back here to this. Yeah, are there questions? Is that clear what we've done here? Yeah? Okay. Sleep mode. Now it works. Yeah, that's again the same thing in the script. So I just simply typed it. But I think it's better if I type it here and interact with you, then it's also for you better to understand it, because if I just show you the code like this, it's a little bit boring. Okay, and this is how we used it. And yeah, it's also on GitHub, so you can check it out. Okay. Note on indirect waits. So what we did here, so inside of this we have used the wait statement. Yeah? So here we called wait. Yeah? And this is when we not call wait in the process that runs here or there. So if we call it like this through a channel, then we call this an indirect wait. Yeah. And then the SystemC thread inside here gets suspended, as we would call wait here inside. Yeah. So therefore we cannot use SC methods. Also this we have discussed, and therefore we need another way, basically, to do this later on. This is when we then use sensitivity list and all of this that we have also discussed already. But we need there some more interaction with the SystemC kernel to get this running. Yeah. So in SystemC there exists already a class SC5O. So we don't have to write our own, but I just did that you understand a little bit how this concept works. And if you want then to use a method, you could also use the non-blocking version of this FIFO. So it has non-blocking access methods. Okay. But I think I want to show you something different. Yeah. And you will see now that this is really flexible, and this is the exercise that we will have on this topic, and this is a pretty long one. And there we will model Petri nets by using SystemC. And a transition will be a SystemC module, and the place with the tokens will be modeled as a channel. Yeah, so we have this place channel, and there you need then some methods to push a token there, to consume tokens, and this will be part of the exercise. Yeah. Okay, let's see. Wie lange haben wir? Bis Viertel vor, ne? Okay, so then let's try at least to get the idea now of the primitive channels. So that's the next topic. So we stay here on the SystemC base layer, but there you see predefined primitive channels, mutexes, FIFOs, and signals. And I want to explain you also this. Yeah, so we have seen that we have these indirect weights, and we want to get rid of that. And then we need a way to communicate with the SystemC kernel that the kernel actually orchestrates all these weightings. This is also something that we have discussed already briefly in the SystemC kernel, where we do the delta cycling. We have an evaluate phase and we have an update phase. And this is basically done with these three things. So we need to call the function update request. There is an update function and a default event function that we have to implement. And we will discuss that later, maybe also not fully today, maybe also then next week. Yeah, so SystemC provides several of these primitive channels already. So this is signal, we know it already. Yeah, so there's SC FIFO, there's SC buffer. SC buffer is similar to FIFO, we'll talk about that. And there's also SC mutex and SC semaphore. So these are primitive channels that are already there, but we can build our own primitive channels, and we will also do that. We will build our own signal, because only then you understand actually how the whole process works and how we interact with the SystemC kernel. Yeah, so, but quickly let's talk about the ones that exist already. So SC buffer is the same thing as an SC signal, but the difference to SC signal is that in SC buffer an event is generated each time the write method is called, even though the value has not changed. And that's the difference to a signal. So if you write to a signal, if you write this to the signal and then you wait for some time and then you write again the same value, no event will be fired. So it will just be ignored because it hasn't changed. Yeah? If you write then 11, then you would have 2 events, actually. But if you have now a buffer, then you would get 2 events. Yeah? And that's the reason why sometimes you need that. You are just interested in, okay, there was a change, or something was happening, but you don't care about has the value changed or not. Yeah? So with SystemC signal, an event is only generated if the old and the new value of the signal are different. And in buffer, it's always firing an event. Yeah, there's SC FIFO. I mentioned that already. It's also templated. And then you have several functions. If you use it like the FIFO as we had it in our custom FIFO, it has a write function and a read function. And there you see that you have implicit weights. But there's also a non-blocking write and a non-blocking read. So it's just flexible, and then you can choose, okay, I will use it or not. Genau. There's also num available, so that's a method that returns the number of data values available in the FIFO at the current delta time, and also the opposite num free that tells you the number of free slots in the FIFO. Yeah. Also for that I have an example on GitHub that you can use. Yeah, what else? Yeah, there is semaphore and mutex. I assume you know what a semaphore is. I don't have to explain you that. But by the way, do you know where this place is? It's a very narrow path in the city of Prague. And there they put this traffic light semaphore. Therefore, I show always this example. So this is kind of a critical section that only one person can pass actually. And if you want to go through it, you have to get the lock basically. So that's the idea of a mutex or a semaphore. And then you can walk through it, and then you can basically unlock. It's really there. So there is a traffic light with the switch here. So probably many people have stuck already there. Then they introduced the system. Yeah. And also this exists there as a primitive channel. If you are interested in that, I don't want to go so much into the details here. It's just for completeness also here. Yeah, also with semaphore, but I want to skip that because of the sake of time. I think it's more important if we talk about signals. Yeah, so why all of this? We discussed that already. We want to provide variability and interoperability in the modeling. Yeah, so we could have two memory channels with the same interface but different implementations. Yeah, so we do the same thing. There's the simple memory that derives from the memory interface, and it's a pretty simple one. But you could also have a more complex memory model, for example. Yeah, so that's the idea. And then you have the same interface, and then you can swap that. So you can take out this model, put another model there, but you don't have to change the code of the rest of the system. That's the idea. Yeah? Okay. Yeah. Then let's see how far we can go. We have still 15 minutes. I want to start to build with you a simple signal that also interacts with the SystemC kernel. So I can just delete everything that I typed now. Okay. Actually, not so much. At least I think I can keep at least the interface to save some time. So we will build now a signal interface, and this is also derived from the SC interface, and it also will have a read method and a write method. I think producer and consumer probably I also just delete. So I think that's clear. And now we will have a class that is called signal. And it should be actually doing the same thing like SC signal. And but if I show you the implementation of SC signal, it's too complex, and it's not reducing on the important aspects, I would say. Therefore, we do it again. So there's a class signal, which then derives from the signal interface, which is also again templated. But it also derives now from, or we derive it from, it inherits from SC underscore prime channel. And this makes now a huge difference. Because if we look into that, you cannot click on it. So somehow my VS Code has some problems with the C++ decoding here, which is unfortunate. Because I cannot look into the SC prime channel thing. Which is sad. But somewhere it should be. building here, that's test. There, so there's SystemC. Where is it? It's probably in SystemC. No, it's not TLM. It's in SystemC, kernel, SC prime. Now it's difficult to find it. Nobody knows where it is when you cannot click on it. There's it. So if you look into that, and you see already it's a little bit much there. But you see there is a method that should be implemented, which is the request update. There's also an update method. Yeah. So you see that if we derive from that, we should implement some of these functions to interact with the SystemC kernel, because the SystemC kernel knows this prime channel interface and then knows, okay, I can communicate with these functions with this custom prime channel. Yeah, so that's why we have to implement now also some things. So first of all, we have our own interface. So we have to implement again a read function. Oops. We have to implement the write function. We have to implement this update function, and this comes from prime channel. That's important. And that's actually a must. Therefore, I don't understand why they have not made this pure virtual. So maybe to have still some flexibility, I don't know. And there is another function that has to be implemented. This is the const sc event. And then this is a reference, default event. And also this must be implemented. So this is kind of the starting point. And we need some, more things. So let's start with the private stuff. So all of this is public. So in the private thing, we have the current value. So that's the current value of the signal. And there will be the new value. So why do we need that? Because we learned that we should only create an event if the value has changed. And therefore we store the current value and the new value, and then we can compare it if there was a change. Then if yes, we fire an event. If not, we do not fire an event. Yeah, and the event itself is also there, like before in the FIFO. So there's an event, the value changed event. And this is already important because here we can name it as we want it. This is not standardized, but for that we have this default event function, and this default event function can then point basically or return the pointer to this value change event. And later on, if you use the signal in a sensitivity list, the SystemC kernel will call this function and get this default event and knows then, okay, if this fires, I have to call this method or whatever. Yeah? And the notification that something fires comes basically from this default event method. But you will see that in a second. Yeah, what else do we need? We need a constructor for all of this. So signal, is the name then of the constructor. So I have not used now the SC constructor thing here because it's not a SC module, so that's not really required. And the only thing that we do now is we set the current value to 0 and we set the new value to 0 just to initialize it with something neutral. So then we have the read function. So if you want to read, we just return the current value. That's it. But writing is a little bit difficult. So when we have the write, we get the value here. So the first thing that we do is in new value, we store this. And now we do a check. If the new value is different to the current value, then we will do something. And now we have to interact with the SystemC kernel. We call the function request update. And this is also implemented in prime channel. So this is the definition, but it's implemented here somewhere. Yeah, I don't care now, but believe me, it's there. And this tells the SystemC kernel, hey, somebody has called the write function, and we should not immediately write, because you remember we have this delta cycling. Yeah, we have the evaluate phase and then the update phase. And only in the update phase we should finally write the actual value. And there we request basically to the SystemC kernel, hey, somebody wrote something to the signal. We want to request an update. So if we go to the update phase, please take care about this. Yeah, so this is just only kind of a, hey, your kernel, somebody wrote here something, please take care about this. Yeah. Okay, and then the kernel later on comes back in the update phase, and that's the reason why we have this update function. And this, we must implement this, so that's important. And I think in SystemC it's again checked, and I don't know if that really is required. But I have it here in my example. So we check it again. Only if this has really changed, because probably it's if you call that write several times or something like that, it might be that it changes and then later on it did not or whatever. Then we check it again. And then we save to the current value the new value. So here we actually perform the write. Yeah. And then we call the value changed event with SC 0 time. And then other processes that are sensitive to this signal get notified. And this is also implicitly done then over the SystemC kernel. Yeah? And that's the whole idea. So I think I will continue that next time when we have lecture. I think next week we will have exercise. Tomorrow there is no exercise because we are on a business travel. So Derek and myself, we are going to a consortium meeting. So therefore I think it makes no sense if I continue that next time, but I will just show you that again in the SystemC kernel, because this is usually an exam question, how this works. But I think next time we can discuss it again. Yeah. So this is the important thing, this picture. Yeah? So we have the evaluate phase, and you remember all processes that are marked as executable will be then evaluated here. So we will execute them, and then they will generate events. So they will call writes. And then when the write function is called, then we call to the SystemC scheduler, hey, we have update requests, please note them. Yeah. And when all processes are done, then we go to the update phase. And then in the update phase, we will go through all these update requests, and then we will call the update functions of the signals. And this is what happens here. So, and when we use this then in a sensitivity list, and this is again then producer and consumer, and I will continue that example. But you see here, there the signal is used in the sensitivity list. Yeah? So the consumer, so this is not a FIFO anymore, this is now just a signal, but the consumer, you see there, it's using a SystemC method now, not a SystemC thread anymore. And this method is triggered by this sensitivity here. And this is sensitive to the default event. So if you write this, SystemC kernel will call the default event function and know then what is the event in this signal that is relevant. And every time we have a value change on this default event, this process here is called, yeah, which runs here. And this is how we basically interact with the kernel. So you need to do three things, and this is important for the exam because this is always the question in the exam. So you have to call request update, you have to implement update, and you have to have a default event. These are the three important things. Yeah? It's also written here again. Yeah? Implement update, implement default event, of course derived from SC prime channel, but these are the important things to do. Yeah? Okay, then I think we are at the end for today. So yeah, thank you very much for listening, and I hope you understood already some basics of how we can model channels in SystemC and how SystemC is doing that. Huh? Okay, question, yeah.
Regarding the exam,
Mm-hmm.
what can we expect? So how would the exam look like? Is it coding? Is it theoretical? Is it?
It's more concepts. Yeah, so you have to explain how this works. Maybe there is some code, like a snippet like this, and there is maybe a line missing or something like that. And then you can write also some pseudocode. Unless we understand it, everything is fine. Yeah, so that's it's not so much important that you have 100% of the syntax, because we have other programming lectures where you proved already that you can program. Yeah. So it's more about the concepts. Yeah. So you don't have to write a full set of SystemC model. Yeah. Does that help?
Yeah, I just didn't know what to expect. So.
Yeah, so I think the exam is more really about the concepts, and that I can see you have understood the concept behind it. So there's usually also something about in TLM later, where we talk about routing, for example. When we have a very complex SystemC model where messages go back and forward, it's important that you understood basically the behavior and the concept, and how the routing is performed, so how we do address calculations and all of this. And it's not so much important about the syntax here. Yeah.
Is it much in the context of SystemC or even more general?
It's basic, it's also more general. So it could also be that we have an exam question about P3 nets, for example. Yeah. But I think SystemC plays a big role in all of this, because that's the main language today to build virtual prototypes. Yeah. But as as I said, so maybe that you get a snippet like this, and then you have to put in some pseudocode. So if you forget a semicolon, I will not subtract you some points. Yeah. Okay. More questions? Because I think we are already over time. Okay, then next week there will be then probably the exercise. So then we will see each other probably the week after again. Yeah? That's because of the traveling, but I think we are good in time so that we can discuss all the topics that we have on the roadmap for this year, yeah? And also next year. Okay, then see you soon. Bye-bye. Thanks.